In the previous video, we talked about covalent bonds, but there's a whole lot more than just saying, oh, you have two atoms sharing electrons and all that. How do they do it? This is going to be another of those good examples of how the scientific method works, because we're going to run to a theory, and then someone comes and says, yeah, but I made this observation, your theory does not explain it. What do? You come up with another theory. And someone will come and say, yep, but, and you have to develop another theory. Years ago, when I was an undergraduate, my mother used to type my cell biology notes. She loved cell biology, and she enjoyed typing. And of course, hey, you want to type my notes? Go ahead, do it. But my mother told me one day, scientists are mean people. All they're doing is trying to prove somebody else wrong. Mom, you don't understand, that's how science advances. By coming up with a theory, well, the theory does not explain everything, we modify the theory. So in this video, we're going to be looking at the first theory explaining covalent bonds. We are going to be doing it in chronological order because it makes sense, okay? But there will be 2 more videos until we get to the most modern theory. So this theory was developed in the 1930s, and before you criticize these fellows, I'd put the name Pauling because he won a Nobel Prize in chemistry, okay? He was no idiot. He just had certain information, and this is the best theory he could come up with. He called it the valence bond theory of covalent bonds. Basically, he says that you form a covalent bond when you have unpaired electrons that are shared by the overlapping of orbitals that have only one electron. So remember hydrogen, you have one electron, if they overlap, now you have the 2 electrons. The only thing he added, because quantum mechanics was already been active, was that these electrons have to have opposite spins, because quantum mechanics says you can have 2 electrons in the same orbital with the same spin. But other than that, you said it's not different from what we have in common up until now. How many bonds? It's determined by the number of unpaired electrons. If you have 2 electrons, you can only form 1 bond. You cannot form 2. If you have 4 electrons, you can form 2 bonds. You cannot form 3. That's common sense. The problem is this works very well to explain the atomic molecules that only have single bonds. Well, most molecules are not atomic. Most molecules have more than single bonds. So this was just a good beginning. Okay? It also explained why noble gases don't bond, because they don't have unpaired electrons, because the outermost shell is already full, right? To understand this, let's look at a bit at how the hydrogen molecule is formed. When the 2 atoms are too far apart, let me explain, the red line is energy. When the bond forms, the molecule is very stable and the energy drops, okay? So you have 2 atoms that have a certain energy, they're too far apart, they don't attract each other. As they start getting closer and closer to each other, an electron starts feeling the attraction from the other nucleus. But it's also feeling repulsion from the other electron. So for the time being, the attraction is stronger and the atoms keep getting closer and closer, lower and lower energy. There's going to be repulsion between the electrons, some repulsion between the nuclei, but still the attraction is stronger until you form a molecule at the right distance. And that's represented by the lowest energy. But if you get them any closer than that, now the repulsion becomes stronger, and all of a sudden you can form a bond, and the energy goes up. So it is only when the 2 atoms are at a Goldilocks distance, not too close, not too far, that you form a covalent bond. Besides the distance, there's another factor, and that is the orientation of the orbitals that determine how much they overlap. Now, of course, when you talk about s orbitals, since they're spherical, orientation doesn't matter because they're always going to be spherical. But when you have p orbitals, notice that if they are in a straight line, they overlap more than if they are at an angle. So that's what I said by the orientation of the orbitals affects the degree of overlap. There's more overlap, this is stronger. So we're going to see that there's two different kinds of bonds. When you overlap two s orbitals, you form a sigma bond. Okay? Now, you could have an s orbital and a p orbital. As long as they are on a straight line like this, they still form a sigma bond. You could have two p orbitals. It's like a head-on collision. As long as you have a head-on collision, you form a sigma bond. And notice in a sigma bond, the highest density, electron density, is going to be formed between the two nuclei. Okay? And they form single bonds. Pi bonds, on the other hand, result by the side-by-side interaction of p orbitals. S orbitals don't have size because they're perfectly spherical. So it has to be two p orbitals, and rather than head-on collision, they're just going to sideswipe each other. Okay? So when they interact sideways, yes, you do have a line between the two, but notice that the electron density is above and below that line. Actually, the nuclei are located in a node. You see, all of the electrons are above or below. There is none between the two nuclei. There is a node that is a plane where the probability of an electron is 0. Now, we said the single bonds are sigma bonds. Multiple bonds consist of both sigma and pi. They have one sigma and as many pi bonds as necessary to make a double or a triple bond. Let me give you an example. Okay, like I said, all single bonds are sigma, multiple bonds are going to have sigma and pi. So we have three molecules in here. Hydrogen chloride has a single bond, oxygen has a double, nitrogen has a triple. So a single bond means one sigma bond and no pi. If you have a double bond, you always have one sigma, so there's only one left, so you have one pi. Triple bond, you always have one sigma, so if you have three bonds, you have to have two pi's. This pretty much just repeating the same thing. So let me give you an example that drives my students crazy. This is a problem that I put in exams whenever I have a class that no matter what, I can tell they're not paying attention to me. They're either talking, they're looking at the ceiling, they're playing on their tablet or something like that. Okay, wait until the exam comes. And I have a version for those particular classes where I have one or two questions like this, that if they didn't pay attention, they're going to miss it. And then we go over the exam. I can guarantee you, from that day on, everybody's paying attention all the time. Because I asked them, how many sigma bonds? They didn't pay attention. They say, oh, sigma bonds are single bonds. 1, 2, 3, 4, 5, 6. Wrong. What do you mean wrong? We said, yes, I agree that single bonds are sigma. That's fine. But we said double bonds are one sigma and one pi. And then they look at me like, when did I miss that? So how many sigma bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, I missed that one before. So they said 7 is actually 9. How many pi's? 2. Identify the following as sigma or pi. Depends on the orientation. This is side by side, right? So that's a pi. This is front-end collision, right? They're different size, but it doesn't matter. That front-end collision, the electron densities between the two nuclei, so both of these are sigmas. Like I said, there's many limitations to the Valence bond model, okay? It's real good to explain the atomic molecules, single bonds, But then when you get into more complicated molecules, you start running into trouble. Think about the word molecule, okay? H2O. You look at the electron configuration of oxygen, 1s2, 2s2, 2p4. That means you're going to have 3p orbitals, 2p orbitals, 3 2p orbitals, 2, 3, 4. So you have 2 orbitals that have ampere electrons. Okay, that's great, because that allows those p orbitals to interact with hydrogen. Yeah, so far so good. You get H2O, that's fine. But there's one problem. P orbitals, if you remember, they're at a 90-degree angle from each other. That's what p orbitals do. Remember, they are in the x-axis, the y-axis, and then from front to back. There are 90-degree angles. But we saw water in the previous video, and we said, well, it has 4 groups because of the lone pairs and all of that. So it should be tetrahedral, which would be 109, but the carbon does have lone pairs, so it's going to be really less. When you do it experimentally, less than 109 actually means 104.5. You don't need to memorize that. What I'm trying to say is 104.5 is not 90 degrees. That's a big difference. So the Valence theory model does not match real-world observations. We're going to need a different model, and we'll see the next model and its limitations in the next video. Once again, you want my worksheets, you want to practice one-on-one, go to the video description, click on the link to my Wysant account, and make an appointment, and we'll work together.